Vidya Madhavan from Urbana-Champaign. She's going to talk about using the technique of scanning tunneling microscopy to measure different topological phases. So please welcome the speaker.
I hope you didn't have too good a lunch. Or at least if you had a great lunch, I hope you had plenty of coffee. I can see you all, even though you think I can't see you. So, so if you do fall asleep, I'll know. Okay. We've had plenty of theory talks, a couple of experimental talks. And my goal in this series of 2 talks, one today and one on Thursday, is to tell you how you can actually realize many of the phenomena that the theorists have been talking about in experimental situations, and how you can unambiguously characterize the properties of these systems using various different experimental techniques. And the particular experimental technique that I use is scanning tunneling microscopy. So in the series of 2 talks, I decided finally how to split it up. So the first talk is going to be focused on how you can use Landau level spectroscopy. That is, you turn on a magnetic field, you get Landau levels, and how you can actually use these Landau levels to learn a lot about the properties of these materials that we're interested in. In today's talk, I'll be mainly talking about homogeneous systems. Well, there are impurities, of course, these are real materials, but on the whole, the system is rather homogeneous. And then on Thursday, I'll get to another technique, which is called quasi-particle interference Fourier transform spectroscopy. And I'll show you what information you can get using that technique. And I'll also talk about 2 different kinds of inhomogeneous systems. And these systems are not randomly inhomogeneous. There are actually 2 kinds. One is a striped system, and the other is a 2-dimensional checkerboard system. Okay? So these are the 2 systems I'll be talking about on Thursday. So I think for me, the most exciting thing about topological insulators is the fact that they've allowed us to look at material systems from a very, very different perspective. So we have to remember that all the materials that we've been talking about the 3D topological insulators have been known for decades. They've been studied for various other properties, notably thermoelectric properties. So these materials are not new, but what we've done is by looking at them from this new perspective of topology, we've been able to learn completely new and different things about these systems. So I would classify topological insulators in the same category as all of these other phenomena, where you had to use a completely different way of thinking about materials and about particles in order to understand them. So as we've all been hearing, if you have a non-trivial topological material, let's say you have a Z2 topological insulator, bulk Z2 topological insulator, and then you put it in contact with a trivial topological material, then at the boundary, you must have a surface state. The fact that you have a non-trivial bulk dictates the presence of the surface state at any boundary of the strong topological insulator. It doesn't matter how you cut it, but at the boundary, you must have a surface state. Now, surface states are ubiquitous. They're everywhere. You see them in many different materials. The interesting thing about these surface states is that they look like Dirac systems, meaning the low energy physics of these surface state electrons is described by a Hamiltonian that looks exactly like the Hamiltonian that describes relativistic particles in free space. Okay? And in particular, for the topological insulators that we'll be talking about, the mass term also goes to 0. So the Hamiltonian is very simple, and the electrons look exactly like relativistic massless Dirac fermions. And that gives rise to many, many interesting properties in these systems. So one of the interesting properties is that unlike normal surface states where the dispersion is parabolic, if you were to plot energy versus momentum, you would get linear dispersion, with this point being defined as the Dirac point. This would be also true for a relativistic fermion in free space. Now, let me just tell you one more thing. If you were to add a mass to this kind of system, then you could simply solve for the dispersion, and this is what you get for a massive Dirac system. And I'll show you in our 3D topological crystalline insulators, we can realize both of these scenarios. Okay? So the difference between a massive and a massless Dirac system is that very close to the Dirac point, you develop a gap, but at higher energies, the dispersion still remains linear. Okay, so just to put these two kinds of dispersions in perspective, I want to remind you that if you have a conventional two-dimensional electron gas with very small spin-orbit coupling, this is what you would see for the dispersion. Now, if you were to turn on spin-orbit coupling, then the two overlapping parabolas split up like this, but at each energy, you still have two electrons, even though they are at different momenta in this case. Now, the difference between these two scenarios and topological surface states is that, of course, one is that you have linear dispersion, but the other is that at any given energy and momentum, you have just one electron. And that electron has a certain spin. It's a chiral electron, meaning its spin is locked with its momentum. Okay, so you can ask what are the essential ingredients to get a topological insulator, meaning a non-trivial Z2, for example. Well, this might be a short list. You need band inversion, and this is what Charlie was talking about this morning. Band inversion would mean that the parity of the bands gets reversed at certain momentum positions inside the Brillouin zone. You need an insulating gap. You need strong spin-orbit coupling. In fact, as it turns out, spin-orbit coupling does two things. It gives you band inversion. At the same time, it also gives you the insulating gap that you're looking for. And finally, you need the symmetry protecting the Dirac node, but I'll tell you about that in a second. Now, one thing I did want to mention is that spin-orbit coupling is not the only way to get band inversion in a system. So all of these systems here are topological materials, and spin-orbit coupling is responsible for band inversion. But in this system, SMB6, actually, it's a very different mechanism. And it's still topological. So as long as you get band inversion and you have an insulating gap, you can have a topological insulator. Okay, now let's talk about the role of symmetry. We heard about this quite a bit this morning. Topological surface states are also called symmetry-protected states. And the reason for this is without a particular symmetries that protect the Dirac node, you can imagine that these Dirac nodes would get gapped out almost instantly. Real materials are very dirty, they have impurities, they have perturbations, and so if you had an unprotected degeneracy, then you would gap it out very easily, okay? But in order to protect the Dirac node, you need a symmetry in the system, and typically in the Z2 topological insulators, the symmetry is time reversal symmetry. And you know, the way you understand it from the perspective of quantum mechanics is that these eigenstates, these two spin up and spin down electrons, are simultaneous eigenstates of the Hamiltonian as well as the time reversal operator. And when you have simultaneous eigenstates, you cannot lift this degeneracy without breaking time reversal symmetry. This is just perturbation theory, for example, right? So this Dirac node is protected by time reversal symmetry. And if you do break time reversal symmetry, then you will get a gap. And at low energies, the spectrum will look like the spectrum I drew earlier, which is a gapped Dirac spectrum. Okay, Now you can ask the question, are there symmetries other than time reversal symmetry that can protect the Dirac node? And the answer, as you heard this morning, is of course yes. You could have other symmetries. And today I'm going to be talking about a particular system in which reflection symmetry is responsible for protecting the Dirac node. Okay, so here's the outline of my talk. I'll tell you about a new class of materials, topological materials, called topological crystalline insulators. I'll tell you how we can measure these materials using this technique called Landau level spectroscopy. And I'll give you three cases, three examples of the kinds of information we can get using Landau level spectroscopy. The first is we can actually tell using Landau levels if you have massive or massless Dirac fermions, and we can clearly distinguish this from a normal two-dimensional electron gas. There's no ambiguity in this. The second thing is I'll show you how we can actually make measurements of the penetration depth of these surface state electrons. So, as you know, the surface state electrons don't live exactly on the surface. They actually penetrate a little bit. They die exponentially into the bulk. Okay? The length scale over which they actually die into the bulk is determined by the bulk energy gap. So if you close the bulk gap, then the penetration depth of the surface state electrons actually increase. And if you were to touch the conduction and the valence band together, the penetration depth is predicted to go to infinity. And I'll show you how we can actually measure this. Okay? This is a very important thing because that's how the materials goes from a topological to a trivial phase. And the third thing is, finally, if I get a chance, I want to talk about how we can measure electron-phonon coupling using Landau level spectroscopy, and hopefully I'll get to the end and I'll talk about the role of disorder. So topological crystalline insulators. Liang Fu and his collaborators predicted in 2011 that this class of materials should exist. That is, you should have a class of topological materials where the Dirac point is protected by some kind of crystalline symmetry, like mirror or reflection symmetry. Very soon afterwards, in 2012, ARPIS studies suggested that this class of materials, lead, tin, selenide, it's an alloy actually, so it's either lead tin selenide or lead tin telluride, where some fraction of the lead atoms is replaced by tin atoms. Okay, it's an alloy. This class of materials is actually belongs to the category of topological crystalline insulators. Okay, and this is ARPIS study. What they found is this is a temperature dependence of ARPIS spectra. So you can't see this, but this is 300 and something Kelvin, and this is very low, 9 Kelvin. As it turns out, in these materials, band inversion is temperature dependent. At high temperatures, the bands are not inverted. At some critical temperature, band inversion takes place. And you can see clearly at high temperatures, there are no surface states. And then at low temperatures, once you have band inversion, you have surface states. Okay, so the crystal structure of these materials is actually cubic. It's very different from the conventional Z2 topological insulators. Here, for example, is tin telluride, one of the material classes that I was telling you about. You can see that there are two mirror symmetry planes in this crystal. One is this and the other is this. So if you just do a simple calculation of what you expect the surface states to look like, then what you'll find is at close to the x and y points in momentum space, you'll get two Dirac cones, a higher energy Dirac cone and a lower energy Dirac cone. So you'll have two overlapping Dirac cones. In the absence of any extra symmetries, these two intersect in a circle and they would get completely gapped out. Okay? But as it turns out, in this material, you have two mirror symmetry planes. These are the two mirror symmetry lines projected onto the surface. And in these two directions, these two cones don't get gapped out, and you have two Dirac points. That's how you understand how you get these mirror symmetry protected Dirac points. So it's a complicated material compared to a Z2 topological insulator, because this is the Brillouin zone, and within the Brillouin zone you have 4 Dirac nodes, 1, 2, 3, and 4. So this is inside and this is outside. Okay? The band structure looks like this. So here's the Brillouin zone again. 1, 2, 3, 4 Dirac nodes. This is an interesting system in the sense that because the Dirac node is so close to the Brillouin zone boundary, here's the next Brillouin zone. And so the Dirac cone in the neighboring Brillouin zone at high energies, they actually merge together and create something called a Lifshitz transition, where you start off with 2 electron pockets, and above the energy at which they merge, you end up with an electron pocket and a hole pocket. Okay, so this Lifshitz transition creates a region of energy where you have a very high density of states known as a Van Hool singularity. Okay. So these materials are very interesting for many different reasons. One is that they actually have, even though they're alloys, they have a large mobility. They're very tunable by temperature, alloy composition, and as it turns out, by strain. Unlike conventional Z2 topological insulators, where the Dirac point is at a time reversal invariant point in momentum space, here the Dirac points are not at time reversal invariant points, so strain could modulate the position of the Dirac nodes. Not only that, and I'll show you this on Thursday, if you think about the way strain modulates the position of the Dirac points, you'll realize that it's the same physics that can give rise to a pseudomagnetic field. So just like in graphene, you can have pseudomagnetic fields in these materials. So here's a cartoon of a phase diagram for one of these topological crystalline insulators. So remember that it's lead and selenide. Here's the tin content. Look at this number, 0.2. 0.2 means that 20% of lead atoms are replaced by tin atoms. This is a highly disordered system. Okay? All right. So as you change the tin content, you go from a trivial phase to a topological phase, meaning that the bands actually close and then open again, and they result in this topological band inversion. Yes. How do you, sorry, say it? Above this temperature? So all I know about the topological invariance in this system is that there is no equivalent of Z2, but I know that the Chern number is plus minus 2.
Right, but usually it's defined at T equals 0.
Yeah, you can define it. Oh, you mean because it's temperature dependent. I'm sorry, I'll have to defer you to a theorist for that. In this direction and in this direction? Okay, let me talk about this first. It's actually interesting. I think there are 2 effects. One effect is obviously that the lattice shrinks as you decrease temperature. But I have a feeling it's more than that. I think there's some phonon modes that are freezing out at low temperatures. But whatever it is, it's a combination of the 2. And you can actually see that the bands close and then open up again. Okay? Yes? Yeah, it's plus minus 2. Oh, the mirror Chern number. Mirror Chern number. Yeah, it's mirror Chern number. Yes?
So then on your map over there, how are you defining whether it's topological or trivial? Is it just solely based on whether it's a gap or not?
No. So unless you're talking about this critical point, there's a gap everywhere. Okay? The question is, oh, you mean which side is topological and which side is trivial? Yeah, so you can do a simple calculation and you can say, oh, normally ignore spin orbit coupling, the px orbital should be above the py orbital, but you add spin orbit coupling and it reverses. So when it switches over, that's topological and the other side is trivial. That's one way of thinking about it.
Higher temperatures? How at higher temperatures?
It's the same thing. The bands close and then they open up again. At the x and y points, the orbital character of the bands has switched. And that's what gives rise to the topological properties.